All right, let's look at another buoyancy situation here. In this case, we have, we're given a piece of wood. We're told of mass M, floats partially submerged in water, just like you would assume, right, for a piece of wood. Then we're asked here, part A, what minimum mass of solid iron hung from it by a string would cause it to sink? Then part B asks, what mass would cause it to sink with a particular acceleration of g over 2 here? And then part C goes on to ask us, is there a way that we could shape the iron to have the system maintain neutral buoyancy? And okay, so let's just start on part A here. So what we're conceptualizing, what you're thinking about here is that we want to have this piece of wood that basically is pulled down into the water. This is water we're in by a mass of iron that's connected to the bottom of it, right? And we want to know, all that they're asking in part A is like, what'll cause it to sink? So let's just say that we're looking for a neutral buoyancy case there, because we're not told like that it's going to sink with any particular acceleration, but to just sink it underneath the surface of the water, if that makes any sense at all. With neutral buoyancy, what that really means is that the system would be in equilibrium at whatever depth I would put it. And I'll let you kind of think about that a little bit. But let's draw that so that our brains have a nice picture to think about. So here's the surface of the water, say, and then I've got just chunk of wood that would not necessarily be under the water if left to its own devices, but I have attached to that wood a chunk of iron here, and Fe is the chemical symbol, right, from the periodic table for iron, so that's why I'm using it there, stuck underneath it. And they just want to know, like, how much, if this is solid, the iron's solid here, what mass do I need there in order to make sure the wood is totally submerged. So this is the situation I have. And nobody's asking me about the tension in the string or anything about that internal force between these two in this particular problem. So I'm going to consider these as a system. And I know that, for instance, just looking at the physical diagram, the wood is going to have a buoyant force on it. I know that the iron is going to have, because it displaces water, right? It's going to have a buoyant force on it. I'll call that buoyant force prime. I know the wood is going to have its own weight. The mass of the wood is given, and I know the piece of iron is going to have its own weight, and I'll call that mass m prime, and that m prime is what we're after, right? So that's just kind of wrapping my head around what are all the forces. I get my invisible forces of weight, and then everything else needs to be a contact force here. And if I'm going to be ignoring the string, right, that's an internal force. If I would look at these separately, I'd have to consider the string and the tension, etc. But I'm going to consider these as a system, and those are the decisions that you have to make. Is if you want to analyze the forces that are internal, then you need to split apart the objects and draw individual free body diagrams. In this case, we're not asked about any of the internal forces, so it is okay to simplify and to look at them as a system. So my free body diagram for the system, and by the system I mean the wood and iron, so that'll be M plus M prime, right? Now we can take those forces from our physical diagram and put them into a free body diagram. So I know that I have my weights downward, M plus M prime G. And then I have my buoyant forces upward. The buoyant force on the wood plus the buoyant force on the iron. I can throw a sign convention on there. This is going to be a case in equilibrium, right? We're looking at this boundary case. Basically, what you could say is that I'm solving for this neutral buoyancy case, for how much iron has to be on there for neutral buoyancy. And then at the end, you can write it as an inequality and say anything greater than this will cause a downward acceleration. And if that's the way you want to think about sinking, then you can write it as an inequality and come up with that way. But it's always simpler to look at an equilibrium case, right? Rather than a dynamic case. So when you can, like, go for the equilibrium setup, because it's really nice to have your acceleration be equal to 0. So that's what we'll do here. I have, no, just applying Newton's second law. My two buoyant forces are upward. I'm going to go ahead and separate these weights out, because I know that I'm going to be looking for M prime, so I got to separate it out anyway. M plus M prime A, and this acceleration is equal to 0 because we're solving for that equilibrium case of neutral buoyancy. Cool. So, second law stuff. Now I'm going to pull in Archimedes and solve for my buoyant forces. And this is really why I'm making this video, is to talk to you guys about that. That's the new stuff, right? So we're going to apply Archimedes' principle. When I have a little AP there, that's what I mean. The buoyant force without a prime there, that's the buoyant force on the chunk of wood. Okay, so let's take this part. The Archimedes principle tells us that buoyant force is equal to the weight of the displaced fluid. Cool. So I can write that as the density of the displaced fluid, that's water, so density of the water, multiplied by the volume of the displaced fluid. All right, so for the wood, that's going to be equal to the full volume of the wood, since the wood is completely submerged. We're not given the dimensions of the wood, but we are given the mass and the density of the wood. So I know that I can represent the volume of the wood, right? So the volume of the wood I can represent by mass divided by density. And I need to then multiply that by G to make it into a weight. Remember that this is the weight of the displaced fluid. And I just want to, if you haven't yet reviewed the density, mass, volume relationship, that you just have to have that. That should be something that you just know for doing these problems, right? Um, so this gives me the buoyant force on the wood, and then I can do the same thing for the buoyant force on the iron. That's also submerged in water. Remember, this is the weight of the displaced fluid that I'm expressing here. And then the volume of water, that'll be equal to the volume of the iron. So I'm not given that volume. I'm asked to actually find the mass. So similarly, now I'm going to just say, well, that volume will be equal to the mass of iron, which I'm calling M prime, divided by the density of iron, which is given as rho prime here, multiplied by G to make that equal a weight. So now I have something I can do here. I can sub in these buoyant force expressions and my Newton's second law equation there, and then I can gather my terms, and I will be able to solve algebraically for M prime. Okay, so we just have algebra. Our physics is done, and we just have algebra from here on out. I'll leave you to work on that part. So this here is really part A that we're working on. Part B, then let's move on, is asking us what mass of iron will cause it to sink with an acceleration of g over 2. So you could say, well, now I could my free body diagram is actually going to look pretty much the same, isn't it? It's just that the mass of iron is going to be different. So when I solve for M prime, I'm going to solve for a different thing. So you could draw a different free body diagram and then call that like M double prime or something, to make sure that that is a different mass. It depends on how you conceptualize it. The big difference here is that for part B, so if I'm doing part B, let's see, I'm going to kind of put that all in one little spot there. So if I'm doing part B, now I can write my second law equation. I still have buoyant force from both. They're still submerged, right? I still have their weights. And how about I'll call this double prime now, because it's going to be a different mass. But now this whole enchilada is accelerating downward, right? We're told that it is accelerating downward. Now, downward acceleration is opposite to the sign convention that I just chose, isn't it? So I have a couple different choices here. I can go back and change my sign convention, but instead what I'm going to do is just remember that I have downward negative, and so my acceleration needs to be negative. So this is going to be equal to M plus M double prime times A. Oh, and A is equal to G over 2. So I can sub that in there. Right. So You can, what I did in the written solutions, if you look at those, you can see that I solved it in general for just a general acceleration, and then I subbed in the downward g over 2. And that was really just to illustrate so that you could see how, like if you were coding this, right, you might want the user to be able to put in different masses and then see the behavior of the system. That's always the more powerful solution, is something that's general like that. But for the purposes of this video, I'll go ahead and follow the question prompt here. So, our buoyant forces that we would sub into this equation would be the same as we found over in part A. So I have both, because we have full submersion, right? In both cases, nothing has changed there. So I can substitute in those buoyant force magnitudes. And then I have, now it's just a little bit more algebra because the right-hand side of my equation is no longer 0. But my only unknown then will still be this m double prime that I can solve for there. As far as part C goes, this is something that I really like for students to think about and kind of discuss there. So whatever, using the mass of iron you found in part B, so this M double prime, that if just, kind of plunked on there in a solid form would cause the whole thing to accelerate downward at G over 2, how could you shape the iron so that you could maintain the neutral buoyancy that you had in part A using this greater amount of iron? And that's just kind of some 3D thinking I want you to consider, and feel free to reach out to me with a solution if you want to run your solution past me.